this experiment, I'm going to describe the current voltage characteristics of various types of diodes, and also I'm going to describe and analyze a half-wave rectifier circuit. For this experiment, we required some materials. We required diode, resistor of 1 kilo ohm and 10 kilo ohm, capacitor, analog board ADLM1000 and multimeter to measure voltage and current. This is my circuit, and here is the diagram of this circuit. In this circuit, I am using this kind of diode. In this diode, you can see there is a silver lines on it. The silver lines indicate that this pin is cathode, which is negative, and this side of pin is anode, which means positive. And we know that diode allows current to flow only in one direction. And the condition in which it allows to flow a current in one direction is called forward bias. In a forward bias, the external voltage source, which is connected to the diode, which is applying voltage to it, the positive side of the external voltage source should be connected to the positive pin of this diode, and the negative side of the external voltage source should be connected to the negative pin of this diode. Then this condition will call forward bias. But this diode is a real diode, which and it's called PN junction diode. So this kind of diode have some barrier voltage, which we also call voltage drop. Suppose the barrier voltage of this diode is 0.7 volt. So to flow current through this diode, the value of the external voltage should be greater than the barrier voltage, or voltage drop means greater than 0.7 volt. Then this diode will allow to flow current through it. If the value of the external voltage source should be less than the barrier voltage or voltage drop, then in forward bias condition also the diode will not allow to flow a current through it. So if we reverse this diode, means the negative pin is now connected to the positive of the voltage source and the positive pin is connected to the negative of the voltage source, then this condition is known as reverse bias. In reverse bias condition, there is no current flow through the diode. If we apply any value of voltage, so voltage through external voltage source, there will be no current flow through the diode in a reverse bias condition. This is my circuit, in which I use the same diode which I showed you. This is my resistor of 1 kilo ohm, and this is all the pins of external voltage source which I am providing through ADLM1000. This yellow wire is connected to a channel A, which is a positive, green is connected to a ground, which is negative, and we clearly see that the positive wire is connected to the positive of the diode and the negative of the wire is connected to the negative of the diode, which means this condition is forward bias. But to flow a current through the diode, our value of the external voltage source would be greater than the barrier voltage, and we will find the barrier voltage of this diode by applying the various value of external voltage to Pixel Pulse 2 software, and we will measure the current of a diode across the resistor through multimeter. So let's get into it. This is my Pixel Pulse 2 software, by which I will provide various input voltage to our diode, and also I am going to measure current which will flow through this diode across a resistor by the help of a multimeter. Currently our input voltage is set to a 0 volt DC, and there is no current flowing through the diode. Now I will set this value to a 0.1 volt. But still there is no current flowing through this diode. This is because this diode is a real diode, and this diode have some barrier voltage or a voltage drop. So when our input voltage is greater than barrier voltage, then this diode will allow to flow current through it. But now our input voltage is less than the barrier voltage. This is why there is no current flowing through it. So let's find the barrier voltage of this diode first. Now I set this value to 0.3 volt, but still there is no current flowing through the diode. Now I will set this value to 0.4 volt, and still there is no current, or there is some fluctuating. This means we are near the barrier voltage, or we call voltage drop. Let's change this value to 0.42 volt. Now as we can see, our current which is flowing through this diode is 0.01 milliampere. So we find the barrier voltage of this diode, which is less than 0.42 volt. So we can say the barrier voltage of this diode is 0.41 volt. So when we apply input voltage greater than 0.41 volt, then this diode will allow to flow a current through it. Or when we and when the input voltage is less than the barrier voltage, then this diode will not allow to flow a current into it, and it will act like a reverse bias condition. Currently our input voltage is greater than the barrier voltage, so diode is allowing current to flow into it, and this condition is a forward bias. Now let's reverse this diode. So when we reverse this diode will act like there will no current flow through this diode, and this condition is called reverse bias condition. In reverse bias condition, we will apply any amount of input voltage, but there is no current flow through the diode. As you can see, I am applying 1 volt of input voltage, but there is no current flowing across the resistor. This means that the diode is not allowing to flow any current. This is because this is a reverse bias condition. Now we will change this value to somewhat 5 volt. Now there is still no current flowing across the resistor. This is because our diode is in reverse bias condition. This is my circuit of half-wave rectifier, in which I use the same diode which I use in part 1. This is my resistor of 10 kilo ohm, and in this experiment I am using 3 pin of ADLM because I am providing AC input voltage to ADLM to our diode. Yellow is connected to a channel A, which is a positive, green is connected to a ground, which is negative, gray is connected to a channel B, which is put between negative of a diode and resistor. The yellow is a positive, which is connected to a positive of a diode, green is a negative, which is connected to a negative of a diode. So this condition is a forward bias. So in this half-wave rectifier, in forward bias, diode convert AC voltage source into a DC voltage source. But to convert AC voltage to a DC voltage, our AC input voltage value should be greater than barrier voltage, which is 0.41 approx. So our AC input voltage value should be greater than 0.41 to convert AC voltage into a DC voltage. This is my Pixel Pulse, which I use to provide various AC input voltage. So let's provide 1 volt of AC input voltage to our diode, As you can see, I'm providing 1 volt of AC input voltage. This is the graph of AC, which is a sinusoidal, positive sign, negative sign, positive sign, negative sign. And this is my output voltage, which is a DC. Diode is converting AC voltage source into a DC voltage source by neglecting all the negative side of sinusoidal. As you can see, in output DC voltage, our diode is providing only positive side of a sign and neglecting all the negative side of a sign. And also you can see our value of AC voltage source is 1 volt, but our DC voltage source is values approximately 0.62. This is because the value of output voltage DC in a half wave rectifier is the formula for this is Vm minus Vd. Vm is the peak value of AC input voltage source, which is 1 volt here, and Vd is the barrier voltage, which is somewhat 0.42. When we subtract this together, we will get 0.68, which is our output DC voltage in a half wave rectifier, as you can see on the screen here. Now we will provide 2 volt of AC input voltage. As you can see, our output DC voltage is approximately 1.6, as I mentioned the formula Vm minus Vd. To make it more clear, DC voltage, as you can see, this is not a appropriate DC voltage, because DC voltage is somewhat a straight line, but this is not a straight line. To make it more clear and to make it more DC, more pure DC voltage, output DC voltage, we will add capacitor in a parallel of our resistor. The more the value of a capacitor, the more pure DC voltage, output DC voltage we will get. This is a capacitor of 4.7 microfarad. Now we will put this in parallel of a resistor. As you can see, our output DC voltage is somewhat more pure, somewhat more near to DC, but this is not a straight line, because my capacitor value is not very big. This is only 4.7 microfarad, but when we applied more large value of capacitor, we will get more pure DC. So by this mean, this circuit is acting half wave rectifier. Here this is my all calculation. The first one is VDC, average DC output voltage. The second one is rectifier efficiency. The third one is ripple factor. To calculate average DC output voltage, our formula is Vm minus Vd by pi. Vm is the peak value of AC input voltage, which here for this calculation I assume it is equal to 2 volt. In the question it is given that Vm is equal to this that, and Vd is equal to 0.41 volt. Vd is equal to barrier voltage for our diode, which we also call voltage drop. And one more thing I want to tell you, that for this half wave rectifier we have used real diode, which is made up of silicon, which is also called PN junction diode. The barrier voltage for this diode is basically 0.7 volt. When we Google, we will find that the barrier voltage for this diode is 0.7 volt, but this is depend upon many conditions like quality of the diode, the room temperature. In our case it is equal to 0.41 volt, but when someone asks you that what is the value of the real diode, silicon based diode, so we will tell 0.7 volt, but in our case we have taken the exact value that what we got. Okay, so by calculating all this, I get the VDC, average DC output voltage, equal to 0.506 volt, and the rectifier efficiency, the formula for this is VDC square by Vm square by 2. By calculating all this, I get the 12.6%. The ripple factor, the formula for this is, and this is all the formula for half wave rectifier and also with real diode. If we use the diode, ideal diode, the formula for all this is different, and we use if full wave rectifier, also the formula will be different. In our case, we use real diode in a half wave rectifier. Okay, so for ripple factor, the formula is VAC square by VDC minus 1, which is all under root under. VAC is AC voltage in AC, which is voltage which is input voltage, which is equal to VRMS, RMS voltage, which is equal to Vm by 2. Vm is peak AC input voltage, which for this calculation I assume 2 volt. So by calculating all this, I get 1.704. This is my part 3. In part 3, I use the same circuit which I use in a part 2 half wave rectifier circuit. There is only difference is that I replace the diode with LED. The full form of LED is light emitting diode, which is also one type of diode. This is the same LED which I use in my circuit. As you can see, there is two big pin. The biggest pin is positive, which is anode. The small pin is cathode, which is a negative, which is same work like a normal diode. Now look into the pixel pulse 2, as I am providing AC input voltage by ADLM 1000, and currently I am providing 0 volt to LED. Now I will change it to 1 volt. As you can see, my LED is not glowing. This is because this LED will work same like diode, and this LED also have some voltage drop, which is also called barrier voltage. When my AC input voltage, value of AC input voltage is greater than the barrier voltage, then our LED will glow. Okay, currently my value of AC input voltage is less than the barrier input voltage or voltage drop. This is why my LED is not glowing. So let's change the value from 1 volt to 2 volt. As you can see, my LED start glowing. So it means that my value of AC input voltage is greater than the barrier voltage. That's why my LED is glowing. And one more thing I want to tell, that the frequency for my this AC input voltage source for this LED is 1 Hz, as it is mentioned in PDF. This. Now I change this value to 4 volt, value of AC input voltage. As you can see, my LED is glowing more brighter. This is because I'm increasing the AC input voltage, and this LED is in forward bias, so current is flowing through this LED, and the current is flowing through LED is 4 volt. As we increase the voltage, the LED will go more brighter and brighter. This circuit is very similar to the circuit which I use in apartment. Only difference in that I am using a Zener diode instead of the real diode, which is a p-n junction diode, and I'm using a resistor of 220 ohm. In PDF it is mentioned it's 200 ohm of resistor, but I don't have that, so I'm using 220 ohm of resistor. Zener diode is a diode which is similar to the real diode. Only difference in that in Zener diode it have breakdown voltage in a reverse bias condition, which is similar to the barrier voltage which is available in a forward bias condition. Suppose the breakdown voltage of this Zener diode is 10 volt. So if we apply an input voltage less than 10 volt in a reverse bias condition, Zener diode will not allow to flow current. But if we apply input voltage greater than 10 volt in reverse bias condition, Zener diode will allow to flow a current in reverse bias condition. Here is my circuit. In this circuit is in forward bias condition. My barrier voltage of this Zener diode is 0.4 volt. If we apply voltage less than 0.4 volt, suppose I am applying 0.3 volt, as you can see there is no current flowing through the Zener diode. But if we apply input voltage greater than 0.4 volt, suppose I am applying 0.45 volt, as you can see current is flowing through the Zener diode because my input voltage is greater than the barrier voltage. Now I reverse this Zener diode. Now my Zener diode is in reverse bias condition, and my breakdown voltage for this Zener diode is 1.5 volt. Suppose I apply input voltage of 1 volt and there is no current flowing through the Zener diode in reverse bias condition. Now I apply current input voltage greater than 1.5 volt. Suppose I am applying 1.9 volt. As you can see current is flowing in a reverse bias condition also, because my input voltage is greater than the breakdown voltage.